Hello guys, Wednesday morning, although it's Tuesday afternoon when I'm doing this, it's actually Wednesday morning to you, so I'm stay confused all the time anymore. Anyway, we're on section 3, page 17 if you have your printout in front of you, and it just talks about how, we're going to talk about the interaction of waves. It talks about how you slip into water in your snorkel gear with your mask on, and you can see clearly across the pool. And as you start to swim, you start the flippers going, and you're disturbing the water, sending ripples moving outward in all directions, okay? And as the ripples hits the wall, it bounces off the wall and kind of travels back towards you, okay? When water waves hits the side of a swimming pool, they bounce back because they can't pass through a solid wall, obviously, okay? Other kind of waves may interact in a similar way when they hit the surface of a new medium, okay? And this type of interaction is called reflection, okay? We talked about this a little bit in astronomy, if you remember, okay? When an object, you're going to see this again, when an object or a wave hits a surface through which it cannot pass, it bounces back. And this interaction with that surface is called reflection, okay? There are many examples of a reflection in your everyday life. Bouncing a ball, okay? It actually reflects and comes back, okay? When you look in the mirror this morning, you use light that was reflecting to see yourself. If you ever shouted in an empty gym or maybe an overhang in the mountains or something like that, the echo you hear was caused by sound waves that reflects off of something else and bounces back towards you, okay? All waves will obey the law of reflection, to help you to understand this law, okay, you're going to look at the picture down there on page 18, and it shows you sunglasses. And what it's talking about, the diagram shows how the light wave travels to make a reflection. The arrow labeled incoming wave represents a wave moving towards the surface at an angle. The arrow labeled reflective wave represents the wave that bounces off the surface at an angle, okay? Then you got the dotted line there, and that's normal, and that line is drawn perpendicular to the surface at the point where the incoming wave strikes that surface. It sounds like a big rigmarole. The picture helps explain it, and I'm going to try to help a little bit better. The angle of incidence is the angle between the incoming wave and the normal, and the angle of reflection is the angle between the reflective wave and the normal, okay? So the law of reflection states that the angle of incident equals the angle of reflection, okay? So basically what that is saying is, you got a pair of sunglasses, and this is the normal coming in, okay? An incoming wave is coming in at this angle. It hits, and it comes off at this angle. The angle, what it's talking about, the angle of incidence, has got to, if it comes in at a 35-degree angle, it's going to come off of here at a 35-degree angle. If it comes in here at a 40-degree angle, it's going to come off at a 40-degree angle. That's what it's talking about, okay? You break it down with all the technical jumbo, it's really not all that hard, okay? Then we move into refraction. Again, I talked about this in astronomy, if you remember. It talks about, have you ever been riding a skateboard and gone off the sidewalk onto the grass? If so, you know it's hard to keep moving in a straight line. The front wheel of the side moving into the grass slows down, but the front wheel on the sidewalk continues to go fast. And that's usually where I go off the skateboard and end up over in the yard somewhere. The difference in the speed of the two front wheels causes that skateboard to change direction, okay? So what causes refraction? Like the skateboard, it changes direction. Changing speed can cause waves to change direction also. When a wave enters a new medium at an angle, one side of the wave changes speed before the other side, and this causes the wave to bend, okay? And the bending of waves due to a change in speed is called refraction, okay? It's kind of like, this is the waves coming down, okay, right here. This is the surface, maybe. It's coming down. These hits first. So this is going to slow down first. These are still going at whatever speed they were coming in. So when it does that, it bends the wave, okay? That's why light, if we took a shoebox and put a hole in the back of the box and took a flashlight and shined through it, yes, the light's going to be more intense coming through that hole, but it's going to bend around and light up that box. Now, the corners will not be as bright, obviously, as the light coming through the hole, but that light will bend around, okay? That light, the waves of the light will bend around and light up the entire box, okay? So when does refraction occur? A wave does not always bend when it enters a new medium. Bending occurs only when the wave enters the new medium at an angle, okay? Then one side of the wave enters the medium first. This side changes speed, but the other side still travels at its original speed. Bending occurs because the two sides of a wave travels at different speed. Even if you don't skateboard, you've probably seen refraction in daily life, okay? Have you ever had trouble grabbing something underwater? Take a glass of water, you know, just clear water, and set it somewhere, and put a pencil down in it. And you know, the pencil, the top part looks like it's here, but the bottom part looks like it's over here. That's refraction, okay? The white light, when white light enters water, different colors of the light bends different amounts, okay? And the white light separates into colors, and that's when you see a rainbow, okay? That's what a rainbow is. You guys knew that, though. Then you've got this thing called diffraction, and sometimes waves bend around a barrier or passes through a hole. That's kind of what we were talking about. When a wave moves around a barrier through an opening in a barrier, it bends and spreads out. And these waves, interactions, are called diffraction, and that's how they bend around. You take a CD and shine a flashlight on it, and you will see, you'll get a rainbow color. And the reason is because of the grooves and all that. Even though you can't feel them with your hands, it's not a smooth surface always. And the light will hit that and reflect in different ways, or refract in different ways, okay? We'll try that when we get back. Interference. If you've ever seen soccer balls collide in a practice drill, the ball bounces off of each other because they cannot be in the same place at the same time. Surprisingly, this is not true of waves. Unlike two balls, two waves can actually overlap when they meet. Okay, and that's the interference. Interference is the interaction between waves that meet. And there's two types of interference. You've got constructive and destructive, okay? The interference that occurs when waves combine to make a wave with a larger amplitude is called constructive interference, okay? You're going to see that again. The interference that occurs when waves combine to make a wave with a larger amplitude. In other words, they're coming together, but they hit and they actually get bigger when they meet. They actually grow larger, okay? That is called constructive interference. You can think of constructive interference as waves helping each other or adding their energies. Okay, so when the crests of the two waves overlap, they make a higher crest. When the trawl of the two waves overlap, they make a deeper trawl. In both cases, the amplitude increases, okay? So destructive interference, the interference that occurs when two waves combine to make a wave with a smaller amplitude is called destructive interference, okay? The interference that occurs when two waves combine to make a wave with a smaller amplitude is destructive interference, okay? You think of destructive interference as waves subtracting their energies, okay? This is where they kind of come together and they kind of, one of them kind of levels out, okay? They don't actually get bigger. They just kind of level each other out, and, okay? So they do interact, they have interference, but they kind of subtract the energy from each other. Neither one of them builds because of it. If a crest has a larger amplitude than the trough, or the crest wins. If the original trail has a larger amplitude, the results is a deeper trail, obviously. If the original wave has equal amplitude than the crest and the trail, then it can completely cancel out, okay? And you'll see pictures of that on page 21. It kind of helps explain that a little bit better with pictures there, okay? Then we go into standing waves. If you tie a rope to a doorknob in continuous shape, that free end wave will travel down that rope, reflect at the end, and come back. The reflective wave will meet the incoming waves. When the waves meets, the interference occurs, okay? If the incoming wave and a reflective wave have just the right frequency, they produce a combined wave that appears to be standing still, okay? This combined wave is called a standing wave. So a standing wave is a wave that appears to stand in one place even though it is really two waves interfering as they pass each other. So even though they're meeting and they're going past each other, they appear to just stand still, okay? They come in, they meet, but neither one of them has the advantage, and they just continue to go. But they look, because of the way they look, it looks like they're just standing still, okay? Then you got nose and anti-nose. In a standing wave's destructive interference produce points with an amplitude of 0, okay, and you'll see that up at the top of page 22. These points of 0 amplitude on a standing wave are called nulls, okay, and you're going to, that's one of your words for today, okay? These points of 0's amplitude on a standing wave are called nulls, okay? The nulls are always evenly spaced along the wave. At points in the standing wave where constructive interference occurs, the amplitude is greater than 0. Remember, that's where it builds on energy. Constructive, it's building on the energy of each other. The point of maximum amplitude on a standing wave are called antinodes, okay? And these are the points of maximum energy of a wave. And they occur about halfway between two nodes, okay? And again, all you got to do is look up the definitions of those, okay? Resonating, talks about, have you ever pushed a child on a swing? At first it's difficult to get him started, but once you get him going, it's pretty easy. Just a very small push will continue to get him going or keep him going. Most objects have at least one natural frequency of vibration. Standing wave occurs in an object when it vibrates at a natural frequency. If a nearby object vibrates at the same frequency, it can cause a resonating sound, okay? That is an increase in the amplitude of a vibration that occurs when external vibration matches an object's natural frequency. You ever seen, I know in the old lunchroom, if you remember, they had the carpet on the wall. It was framed out, you know, and all that. It was there for a reason. It actually helped because the noise would resonate off the walls and all this stuff, right? And it would get really loud. And that carpet was put there to absorb some of the sound waves. Believe it or not, that's what it's for. And it does work to some degree. You get 200 kids in there and everybody's screaming at the top of their lungs. It takes a lot of carpet, especially on a tile floor. Think about it, if you walk into an empty room with no furniture, no drapes on the over the windows, nothing on the wall, your voice really amplifies, right? It resonates off of everything, it seems like. But when you start putting furniture in, carpets down, you're hanging curtains, all that helps to absorb some of that sound, okay? And we'll talk about that a little bit later on also, okay? Again, take your time, look the words up. They're in bold print. The words, all you gotta do is kind of match up with the definition. I mean, I'm giving this multiple choice, so take your time, do well. Okay, again, as we talked earlier yesterday, just because you're remote doesn't mean your grades don't count. Okay, you still want to do well. You want to do your work. Everything you do, you should do it to the best of your ability. Okay, you guys are bright. You're smart kids. Don't get slack. Okay, keep working hard, and I will see you later. Bye.